Hello friends, IBM is here to bring you an episode of Learning Physics, and today I would like to introduce the formation of solids. This could be about three parts of the formation of solids. Note that in the formation of solids, the main concepts rotate around Hooke's law, stress, strain, and Young's modulus, and maybe elastic potential energy. So this is unit 6, although we are not answering these units in their order. This is supposed to be unit 6. Do not forget the document. The document is in the video description, or there is a link to the documents of multiple choice questions in the video description. These multiple choice questions are from past papers in the years between 2022 and 2001. Therefore, you can look at those papers in that range. So the questions are from those papers, and therefore these are going to be very good questions for your practice. Do not hesitate to download the papers and practice on the hard copies after printing. Without wasting time, let's go to the document and start solving these questions under the formation of solids. So here we are in the formation of solids, and the first question is: identical springs are joined in 4 arrangements. Which arrangement has the same spring constant as a single spring? Let's first find a single spring. Let's have a single spring with a load L, I'll call the load L attached to the spring. Let the constant of the spring be K. If the spring has a constant K, let its extension be E. So by Hooke's law, the load L is going to be equal to K times E. So the spring constant here, K, is L over E. Now let's look at these arrangements. This one, the load L is attached. Of course, this will extend by an extension E, and this one also extends by an extension E if they're in series, which means total extension, which I'll call E total, is going to be twice E. But know that the same load L is attached. So by Hooke's law, the load L should be equal to the total constant K total times total extension E total. So the load L is equal to total constant, which I'm calling K total, times extension, which is twice E. Remember, L is Ke. So I'll just substitute for L here. So L is going to be Ke is equal to K total, then times twice E. So E has cancelled. You notice that total constant K total is going to be 1 over 2 times the constant of 1. So the total extension here is a half K. Then here in the second case, if one spring extends by E when it is used alone, it means when they are used when they are two in parallel, each spring will extend by a half E. So this one extends by a half E, this one extends by a half E. That means the total extension of the system is just a half E. Then by Hooke's law, load is equal to total constant K total times total extension, which I've said is a half E, which means, remember, L is Ke. So which means K times E is equal to total constant K total times a half E. So this means that E again has cancelled. So it means total constant K total is going to be 2 times K. So total constant is twice the constant of just 1. Okay, so that is not the answer. Let's check C. C is each of these, because they're in series, so this extends by E as we have seen in the A, this also extends by E, this extends by E, this extends by E. So this branch has an extension of 2E as we have seen in part A. This one also has an extension of 2E. But remember, when springs are in series, in parallel, the total extension is half the extension of just one. So that means total extension here is going to be half of 2E, which is just E. Half of 2E, which is just E. Then the load, remember, will be equal to total constant, then times total extension, which is E, but the load is Ke. So we have that K times E is equal to K total, then times E, which means that K total is the same as K. So our answer is going to be C. We can also establish the total constant. Here, remember, these two springs are in parallel, each extends by a half E. So the total extension here is a half E. Total extension here is a half E. Then this one will extend by E. So total extension for the whole system is going to be a half E plus E, which is 3 over 2E. If I wanted the spring constant, I will just say load is equal to total constant times extension, which is 3 over 2E. But remember, the load is KE. So I will say that K times E is going to be equal to K total times 3 over 2E. And E cancels out. So that means total constant is going to be 2 over 3 times K. You will notice that as we saw in the deformation of solids in paper 2 questions, that always there is a relationship between the spring constant and the extension. In other words, if I know the extension, total extension, then the reciprocal of the coefficient of the extension is going to be equal to the coefficient of the total constant. For example, here the total extension was 2e and the coefficient here is 2. So, and you notice that the total constant is a half k. That means a half is the reciprocal of the coefficient of 2. In the second case, the total extension was a half e. The coefficient here was a half, and the reciprocal of a half is 2. That's why you see the total constant is 2k. In part C, the coefficient here was 1, and of course the reciprocal of 1 still remains 1. That's why you see the total constant is just k. In part D, the coefficient for the total extension is 3 over 2e. Then the reciprocal of 3 over 2 is 2 over 3k. 2 over 3. That's why you see now the total constant is 2 over 3k. So there's a relationship between the extension and the spring constant by looking at their coefficients. Okay. An unstretched spring has a length of 2 centimeters. The spring is then stretched within its limit of proportionality by a tensile force of 1.5 newtons, so that the elastic potential energy stored in the spring is 0.045 joules. What is the stretched length of the spring? Okay, so we know that the elastic potential energy, E potential energy, is equal to a half times F times X. So we can find X. Of course, the energy is of making X the subject and substituting. X is going to be 2 times the elastic potential energy, which is 0.045, then divide by F, which is 1.5 newtons. So this gives us the value of X, 2 times 0.045 divided by 1.5. That gives us 0.06 in meters, 0.06 in meters, which is the same as 6 centimeters. So that is the extension, but we want the stretched length of the spring. The original length is 2 centimeters, so the stretched length L is going to be the original length plus the extension, which is going to be 2 centimeters plus 6, which is equal to 8 centimeters. So our answer here is going to be D. That is the stretched length. It is the original length plus the extension. A non-tensile force acts on a metal wire. The wire does not exceed the limit of proportionality. That means Hooke's law is obeyed throughout. Which two measurements enable the strain of the wire to be calculated? Remember, strain has been defined as extension over original length. Or we also know that Young modulus is equal to the stress divided by strain, where stress is equal to force over area. So let's check the options which are available. The unstretched length of the wire and the cross-sectional area, that will not give us the strain. The unstretched length of the wire and the extension, that is strain, extension over original length. So our answer is going to be B. The wire is extended by different forces. The wire obeys Hooke's law. A graph is plotted to show the variation of a quantity y with a quantity x. Variation of y with x. What could x represent? What could x represent? So first of all, we are going to eliminate B and C, because if Hooke's law is obeyed throughout, this would be a straight line. If it is extension against force or force against extension, for force against extension or extension against force, it would be a straight line, because the limit of proportionality is not exceeded and force is directly proportional to extension. So that one will be out. We have eliminated the C and B because this is not, what is given is not a straight line. Then let's look at A and D. A is saying extension, elastic potential energy against extension. So elastic potential energy is equal to a half F x. Elastic potential energy is a half Fx. Elastic potential energy can be a half Fx, or elastic potential energy can be a half Kx squared. And when you look at those two expressions, you notice that elastic potential energy is directly proportional to the square of the extension. But remember, the limit of proportionality cannot be exceeded. That means there is a limit on x. There is a limit on elastic potential energy, because if we go beyond the limit of proportionality, then we have gone beyond elastic. The energy there will not be elastic potential energy, it will be just the work done in stretching the material. So there is a limit on the elastic potential energy. Therefore, the graph must become horizontal to show that there is a point where the elastic potential energy does not exceed, or it becomes constant, that even if x increases, what you'll be obtaining will no longer be elastic potential energy. Therefore, our answer is going to be A, as opposed to D. D is showing on the y-axis we have extension, and on the x-axis we have extension, and on the y-axis we have this is saying on the x-axis we have extension, on the y-axis we have elastic potential energy. Yet A is showing that here on the y there is extension, and on x we have elastic potential energy. So we cannot extend the material infinitely. So there's a point, if we extend it further and further, we shall reach the elastic limit. Therefore, there will be a limit on the extension. That's why the graph is becoming horizontal. Therefore, we have a maximum elastic potential energy at a certain point. And also, I think that is enough. That is enough to explain why it is going to be a elastic potential energy on the x-axis against extension on the y-axis. A copper wire of length 3.6 meters and diameter 1.2 millimeters is stretched by a force of 37 newtons. The wire obeys Hooke's law. The Young modulus of copper is 1.17 times 10 power 11. Which extension is caused by this force? Okay, so we all know that Young modulus is force over area times original length over extension, or stress over strain. So we want to find the extension. What extension is caused by this force? Extension is the only unknown here, so I'll make it the subject. E will be equal to the force, which is 37, original length, which is 3.6, divided by cross-sectional area, or they gave us the diameter. We know that area is equal to pi d squared over 4. So I'll take the 4 up, so I will say times 4, and in the denominator I will have pi times the diameter, 1.22 times 10 power negative 3, and this is squared. Then again times the Young modulus, so this is going to be times 1.17 times 10 power 11. So for my calculator I will have 37 times 3.6 times 4 divide by open brackets. I'll say open another bracket. Okay, pi, open another bracket, 1.22 exponent negative 3, and this is squared, times 1.17 exponent 11, and I will square that. I will close that bracket. This is giving me 9.7 times 10 power negative 4 meters. 9.7 times 10 power negative 4 in meters. The answers are in millimeters, so I will multiply this by 1000, which is 0.97 in millimeters. So our answer is going to be C. A spring has spring constant K. The spring obeys Hooke's law and experiences extension X when a force F is applied to it. The resulting elastic potential energy of the spring is EP. The diagram shows two of the springs joined together in parallel and hanging from a fixed beam. What is the extension and total elastic potential energy of this arrangement when the same force F is applied? Remember, we have said for a single spring, the force F is equal to K times X for a single spring. For the two springs, the extension is going to be less than a half. The extension reduces and it is going to be a half of X. It is going to be a half of the extension of just one. If we had a 3, it will be a third of the extension of just one. If we had 4 springs in parallel, it will be a quarter of the extension of just one. So the extension goes on reducing as we include more springs in parallel. So the extension is a half X, so we ignore C and D. And then the total elastic potential energy, remember we know that elastic potential energy is a half K or a half F times extension. So total extension, remember, is a half X, so this will be a half of F times a half X, which becomes again a half times a half Fx, and this would have been the elastic potential energy for just one spring. So this is going to be a half times E times P. Remember, the elastic potential energy of just one spring is a half Fx. So we have this a half and this a half, so that's why I have a half EP. So our answer is going to be A. A metal wire is stretched, the wire obeys Hooke's law. Which quantity has a value that does not change? Of course, that is Young modulus, so the answer is D. That one does not change because the wire obeys Hooke's law. The Young modulus does not change. It is a constant. An object is stretched until it reaches the elastic limit. Which statement describes the stress on the object when it is at the elastic limit? Remember, stress I think is written as sigma is equal to force over area, which is force times 4 over pi d squared, because area is pi d squared over 4. It is the maximum stress for which the object obeys Hooke's law. The elastic limit, that's not the maximum stress. It is the maximum stress that can be applied to the object before it has elastic deformation. The object already has elastic deformation before we reach there. It is the maximum stress that can be applied to the object before it has plastic deformation. That is true. The moment we go beyond the elastic limit, we have entered plastic deformation. So our answer is going to be C. Two wires, P and Q, are made from the same metal and hang vertically from a steel girder. Wire Q has half the length and twice the diameter of wire P. Identical masses are attached, that means we are applying the same load to the bottom of each wire. Both wires obey Hooke's law as they are stretched and by the weight of the masses. What is the ratio extension of wire P over extension of wire Q? So I will start with wire Q because actually I will start with wire P because wire Q has half the length and twice the diameter of wire P. So from Young's modulus, because from the same method, the Young modulus is the same. And I know that Young modulus is stress over strain, where stress is force over cross-sectional area. Then divide by strain, which is extension of original length. So we get the reciprocal, so it is times original length over extension. So it means the extension therefore is equal to a force original length over area times Young modulus. But remember they have mentioned diameter. So diameter is, area is pi d squared over 4. The 4 goes up. So this will be 4f L naught over pi d squared times E. So we are going to come up with the two equations. Extension of wire P will be 4. The force, the load is the same F. Let the original length of this wire be L naught. Divide by pi d squared times Young modulus E. Then this will be divided by, so I will get the reciprocal. This will be divided by, for wire Q, the load is, this is going to be 4, the same load is applied. Wire Q has half the length of wire P, so this where there is L naught, I'm going to put there a half L naught. Divide by pi, where there is diameter, I'll put there twice D, so this will be twice D and T squared, that times Young modulus E. So remember I'm going to cross multiply and I get the reciprocal, so I have most of these I've cancelled out, but I know some of you will not see the algebra, so I have F for F L naught divided by pi D squared times E, then times the reciprocal, which is pi times 4 D squared times E, divide by 4 F times a half L naught. Some of these quantities are going to cancel out. For example, 4 cancels out, F out, L naught out, pi has cancelled, D squared has cancelled, E has also cancelled. So I have remained here with the 4 in the numerator, divide by a half, which becomes 8. So this is 4 over a half, which becomes 8. So the ratio here is going to be 8 over 1. The ratio here is going to be 8 over 1, which makes the answer to be A. Which statement about elastic and potential deformation must be correct? Number 1, elastic deformation and plastic deformation are proportional to the applied force. That is not true. Remember for elastic deformation, the material can go back to its original length when the deforming force is removed. Plastic deformation, the material cannot go back to its original length. In fact, the material retains its new length, or it retains a length when the deforming force is removed. So elastic deformation and plastic deformation cause no change in volume. Plastic deformation causes a change in volume. So that is not correct. Elastic deformation causes the heating of the material, but plastic deformation does not. It is actually the reverse. Elastic does not, plastic causes heating of the material. Elastic deformation is reversible, but plastic deformation is not. So the answer is going to be D. Plastic deformation, the material does not go back to its original length. So the answer is D. A diving board of length 5 meters is hinged at one end and supported 2 meters from this end by a spring of spring constant 10 kilonewtons per meter. A child of mass 40 kilograms. So this is the child. Therefore, the force here is going to be 40 times 9.81. That is the weight. So if the child is there, there must be a tension force here, which is because the board moves downwards, the tension must be upwards. There must be tension force there in the spring, which tension is going to be given by Hooke's law. The tension in the spring is going to be given by Hooke's law, which is K times X. What is the extra compression? That is going to be X of the spring caused by the child standing on the end of the board. Now, if we consider the diving board horizontal, it means there is equilibrium. So we are going to take moments about the hinge. So moments about the hinge, moments about the hinge. It means the weight of the ball is causing a clockwise moment and the tension, an anti-clockwise moment, and the tension is going to cause a clockwise moment. So we are taking moments. So for the weight of the boy, which is going to be 40 times 9.81 times the perpendicular distance from this point where we are taking moments, which is 5 meters. So that is times 5 meters should be equal to the tension, which is going to be K times X. The tension is K. I'm using tension here, which is Kx. So the tension is going to be K, which is 10,000 newtons per meter, then times X. So we are trying to find X. Sorry, the tension is Kx. So K times X, then this is the force, then times the perpendicular distance of the tension from the hinge, which is 2 meters. So we shall just solve this. 40 times 9.81, that is the force, times the perpendicular distance, which was 5, divided by 2 times 10,000, which gives us 0.0. So X here is 0.0981. This is in meters. So we change to centimeters by multiplying this by 100, which gives us 9.81. So X is equal to 9.81 in centimeters. Therefore, the answer is going to be C. A metal wire obeys Hooke's law and has a Young modulus of 2 times 10 power 11 pascals. The wire has an original length of 1.6 meters and diameter 0.48. What is the spring constant? So we know that Young modulus E is equal to stress, which is force over area, times divided by strain, which is going to be extension of original length. But since we are dividing, we get the reciprocal. So it will be original length divided by extension. So remember force. The force is going to be K times extension. The force is K times extension according to Hooke's law. F is equal to Kx or Ke. So this is going to be equal to K times extension times the original length, then divided by cross-sectional area times extension. So note that the extension has actually cancelled out. So this is going to be equal to K, and remember also that the area is equal to pi d squared over 4. So this is going to give, the 4 goes up, so it will be 4k L naught divided by pi d squared. So let's substitute the Young modulus. Let me just make K the subject. So K is going to be equal to Young modulus times pi d squared divided by 4 times L naught. So I will substitute Young modulus is 2.0 times 10 power 11 times pi. Diameter is 0.48 times 10 power negative 3, but this should be squared. Then divide this by 4 times L naught original length, which is 1.6. So from our calculator, we have 2 exponent 11 times pi, then times 0.48 exponent negative 3 squared, divide by open bracket 4 times 1.6, which is 700 pi, which is giving us 22619 or 2.3. So this is 2.3 times 10 power 4. Yes, 2.3 times 10 power 4 newtons per meter. So our answer is going to be B. The wire is being stretched by a tensile force. Which statement about the elastic limit must be correct? Elastic limit. Number one, the deformation is plastic after the elastic limit. That one is very true. The moment we go beyond the elastic limit, the deformation becomes plastic, where the material now will retain its new length. It will retain some extension if the deforming force is removed. So without checking others, the answer is going to be A. A steel wire has length 300 centimeters and cross-sectional area 0.5 millimeters squared. The Young modulus is 2 times 10 power 11 pascals. One end of the wire is attached to a fixed point. A load 10 newtons is hung from the other end and the wire obeys Hooke's law. What is the extension of the wire? So we know that Young modulus is going to be force over area, that is stress, divided by strain divided by strain, which is extension of original length, where I get the reciprocal, so it is original length over extension. So I want to find the extension, so I will just substitute. Young modulus is 2 times 10 power 11 is equal to the force, which is 10 newtons. Original length is 3 centimeters, which is 3 meters, so that is times 3 meters. Divide by cross-section area is 0.5. We change this to meters squared, so it will be 0.5 times 10 power negative 6. Millimeters squared to meters squared, that is 10 power negative 6, because 1 meter is 1,000 millimeters. That means 1 meter squared is going to be 1 times 10 power 6 millimeters squared. Now if I'm changing from millimeters squared to meters squared, this becomes times 10 power negative 6, or I divide by 10 power negative 6, 10 power 6. Therefore, this will be 0.5 times 10 power negative 6, then multiply this by E. So I'll just press my calculator and make E the subject. So to make E the subject, I'll have 10 times 3 divided by, open brackets, 0.5 exponent negative 6, and another bracket which will have 2 exponent 11. So this is giving me 3 times 10 power negative 4. That is 3 times 10 power negative 4 in meters. So our answer is going to be C. The extension of a copper wire is measured. The extension of a copper wire is measured for different forces for different forces applied to the wire. A graph is plotted to show the variation of the force on the wire against extension. The maximum force applied at point P, the maximum force is applied at point P. That could be the braking force. Which statement must be correct? A is saying point R is the limit of proportionality. For the limit of proportionality, it is supposed to be a straight line. So S is the limit of proportionality here. S is the limit of proportionality. The elastic potential energy of the wire at point S is given by the area under the graph between point T and S. The elastic potential energy at S is the area under the graph. That is very true. Elastic potential energy will only be the area under the straight line part of the graph. So this is very correct. So the answer is going to be B. There is no plastic deformation between points Q and P. It is already there because it is no longer a straight line. The wire obeys Hooke's law up to a point between R and Q. That is not true. R and Q, it must be a straight line if Hooke's law is obeyed. So it obeys Hooke's law between T and S. And where Hooke's law is obeyed is where we find the elastic potential energy. And it's where we find the spring constant, or the constant of the material. Okay, so the answer is B. An extension force, graph for a spring is shown. What is the spring constant of the wire? So this is very easy. Find the spring constant. K is equal to the load divided by the extension. So the load is 6 newtons divided by the extension, which is 15 times 10 power negative 2. So 6 divided by 15 exponent negative 2. That is giving us 40. So our answer is going to be D. is extended by a force. The graph shows how the extension of the wire varies with the force applied. Initially, a force W gives an extension D. A force W gives an extension D. The force is then increased to twice W. This increases the extension to twice D. Which area of the graph represents work done by the force when the force increases from W to twice W? Okay, so work done is always the area under the graph, but is the area with the extension axis. Work is the area with the extension or the length axis, with the extension axis. Work done is the area with the extension axis, not with the force axis, it is with the extension axis. So we want the work done from W by the force from W to twice W, which is going to be this area here. The area with the extension axis, which is a trapezium. So it is going to be the area between T, M, R, and S. Let's see. So here the answer is going to be D. The area between T, M, R, S. That is the work done. Remember, always you look for the axis where there is extension, and the work done is always the area with the extension axis, not with the force axis. So the answer is going to be D. The graph shows the effect of applying a force up to 5.0 newtons to a spring. The spring obeys Hooke's law for forces up to 7 newtons, so it can still continue up to 7 newtons. What is the total extension of the spring produced by a force by a 7.0 newton force? So they didn't show us a 7.0 newton force here, but it's very easy. We can still just find the constant of the spring. So the constant is going to be equal to the load over the extension according to Hooke's law. So I will just use the load which is given here, which is 5 newtons. It is 5 from 0 to 5. Extension is going to be 14 minus 11 caused by 5 newtons, which is 3. So the extension is 3 times 10 power negative 2. So that is the constant. Now again, using the same formula, F is equal to K times X, I will find X. F is 7.0 this time. K is a constant, so it is 5 over 3 times 10 power negative 2. Then times the extension X. So I will just make X the subject. So it will be 7 times 3 exponent negative 2. Then divide by 5. The answers are in centimeters. So I will say, okay, this is X is 0.042 in meters. I multiply it by 100 to check it in centimeters, which is 4.2. So this is 4.2 centimeters. So our answer is going to be A. A rubber cord hangs from a rigged support. A weight attached to its lower end is gradually increased from 0 and then gradually reduced to 0. The force extension curve for contraction is below the force extension curve for stretching. So we have seen this in your class. You must have seen this hysteresis behavior of rubber or of polymers. So what does the shaded area between the curves represent? Note that the total area between the stretching curve and the x-axis is the work done in loading. Then the total area between the contraction curve with the x-axis is the work done in the unloading. The difference between two is the energy which is wasted, or is the energy which is converted into thermal energy, or it is the energy which is not returned. It is the energy dissipated. Therefore, as is saying the elastic potential energy stored in the rubber cord. Elastic potential energy stored in the rubber cord. That is not true. B is saying the thermal energy dissipated in the rubber cord, and I'm saying the answer is B. The energy which is not returned when the deforming force is removed. So it is converted into other forms such as thermal energy. So the answer is going to be B without wasting time. The stress strain graph for a wire is shown in the figure here. So you can look at it is initially a straight line. Initially, Hooke's law is obeyed. What is the Young modulus of the material? Of course, for Young modulus, we just look at the straight line part, and we know that Young modulus is equal to stress divided by strain. The stress is 2.1 times 10 power 8. The strain is 1.4 times 10 power negative 3. So it is 2.1 exponent 11, exponent 8 divided by 1.4 exponent negative 3. So this is giving us 1.5 times 10 power 12. Is it 1.5? Let's check it again. 2.1 exponent 8 then we divide this by 1.4 exponent negative 3. Okay, so we're getting 1.5 times 10 power 11. So this answer is 1.5 times 10 power 11 pascals. So the answer here is going to be D. The diagram shows a force extension graph, a rubber band, as the band is extended and then the stretching force is decreased to 0. What can be deduced from the graph? The rubber band does not return to its original length when the force is decreased to 0. It is returning, but is following a different path. That's what we call the hysteresis. The rubber band obeys Hooke's law for the extension shown. It doesn't, because it's not a straight line. The rubber band remains elastic for the extension for the extensions shown. It remains elastic for the extensions shown. I think this is the answer. Let's check the last one. The shaded area represents the work done in extending the rubber band. Not at all. The shaded area shows the energy which is being dissipated. So the answer is going to be C. The rubber band remains elastic for the extensions shown. It does not go beyond, it remains elastic, meaning it goes back to its original length, but this time it follows a different path. So it remains elastic. Okay. A metal wire of cross-sectional area A and unstretched length L is subject to stress sigma. Remember, stress is equal to force over cross-sectional area. As a result, it has a strain epsilon. Remember, epsilon is equal to extension over original length. And the original length has been given as just L. Which expression gives the Young modulus of the metal? So Young modulus is equal to stress over strain, which is going to be equal to the force, or we don't have the force in the expression, so I will leave in strain there, stress there. So this is going to be equal to, okay, they just gave us, we have stress over strain, so the answer is C without wasting time. Because we don't have area, we don't have load, so this one is showing strain over stress, which is not correct. Two identical springs are connected in parallel. A weight of 8 newtons is hung from the combination as shown in the diagram. The graph shows the variation with the length of the force applied to one spring. The examiner makes this bold, so we can find the extension for just one spring. From here, from the graph here, the extension of one spring, extension if it is alone, extension E for one. Let me just call it E for one spring. If it is used alone, E for one spring is equal to 10 minus 4, which is equal to 6 centimeters when the load is 8 newtons. If it is one spring. Now we have earlier on seen that when springs are used in parallel, the total extension of the system becomes half the extension of just one. So what does this mean? It means the total extension when they are used together for the same load is going to be 6/2. Half of the spring extension of one spring. So that means the extension here is going to be 3 centimeters when they are used both. What is the strain energy in one of the springs? So strain energy in one of the springs, let's first of all find the total strain energy when they are used together. Strain energy is going to be equal to a half. It is going to be equal to a half times the total load, or it is a half Fx. So it is going to be a half times the total load, which is 8, times total extension, which is 3, times 10 power negative 2. And this is going to give us a half, which is 0.5 times 8 times 3 exponent negative 2. So this is going to be the total extension when they are used together. Total elastic potential energy or total strain energy is 0.12 joules. So it means this total elastic potential energy is stored in the two springs. So it means each spring. So I'll say for one spring, the energy stored is going to be 0.12 divided by 2, which is going to be 0.06 in joules. So our answer is going to be A. Note very carefully that if I had used this graph here to find elastic potential, the strain energy in one spring, I would not get the correct answer, because this would give me the elastic potential energy if the spring is just used alone. But then if they are used together, then I have to get the total elastic potential energy or strain energy using the effective extension. Then I will divide the elastic potential energy or the strain energy into 2 to get what is stored in one spring. So the answer is going to be A and not any of those. 3 springs are arranged vertically as shown. Remember, when they are in parallel, their total extension is a half E. And when it is in series, the extension is, let's check here. Springs P and Q are identical and each have spring constant K. Springs R, a spring R has spring constant 3K. What is the increase in the overall length of the arrangement when a force W is applied as shown? So let's assume a force W was applied on just one spring of spring constant. A force W is applied on one spring of spring constant K. It means W would be equal to K times the extension of this spring, which I'm going to call E, which means the extension of just a spring of spring constant K extends with a force. It has an extension which is W divided by K. Okay, so now here the total extension for this, because the constant here is, each of them has constant K. If they are two in parallel, their total extension is going to be a half K. A half E. And the spring constant of R here, spring constant of R is 3K. Remember, we have said extension, there's a relationship between the extension and the constant by looking at the coefficient. If the extension was half E, total constant of P and Q is actually twice K, because we get the reciprocal of the coefficient. Now, if the spring constant is 3K, it means this spring whose spring constant 3K has extension, which is going to be 1/3 times E. So the extension here is going to be 1/3 times E. I've just got the reciprocal of the coefficient of the constant. Remember that simple skill every time. So total extension is going to be a half E plus 1/3E, because they're in series. And this gives us, I think this gives us, okay, LCM is 6. So 3E plus 2E, which is 5E. So total extension is 5E. So the question is, what is the increase in the overall length of the arrangement? In other words, what is the effective extension? So total extension is going to be 5/6 times E, which E is W/K. So our answer is going to be A. 5/6 times W/K. So our answer is simply A. Note the skill here very well because we have discussed this several times in deformation of solids paper 2, and we are now applying it here. A length of metal wire is attached to a fixed point and hangs vertically. Masses are suspended from the wire. Assume the cross-sectional area of the wire remains constant. A stress-strain graph for the wire is plotted as shown. What is represented by the shaded area under the graph? The shaded area under the graph. So, first of all, this is the shaded area is giving us actually stress. Actually, the area is going to be equal to a half times the stress, then times the strain. So area is equal to a half. Remember the stress is force over cross-sectional area, then times, no, let me just write here word area so that people don't force me to cross out A. So area is a half times force over cross-sectional area. Area over under the graph is a half times force over cross-sectional area of the material. Then times strain, which is extension over original length. And you and me note that area times original length is volume. So the area under that graph is going to give us a half times F times extension, then times 1 over cross-sectional area of the material times its original length gives us volume. So this is over volume. But a half Fe is elastic potential energy or strain energy. So the area under the graph is therefore showing us the elastic potential energy divided by the volume. So let's see the options which are there. It is showing strain energy. That's not true. Strain energy, remember strain energy is elastic potential energy. Strain energy in the wire over cross-sectional area, that is not true. Strain energy in the wire of original length, that's not true. Strain energy in the wire over original volume of the wire. So the answer is going to be D. Which spring combination has an overall spring constant of 8.0 newtons per meter? Okay, so remember the constant, spring constant K is going to be equal to the load over total extension E total. Let's check here. For the first one, we have this one is going to be the load, which is 1.6 divided by total extension, which is 2 plus 2, which is 0.4. 2 plus 2, which is 0.4. So I have 1.6 divided by 0.4. That gives me 4. Yet we want it to be 8. So that one A is out. You can check this one. So this one is constant here is going to be 1.2 divided by effective extension, which is just 0.075. 1.2 divided by 0.075, that gives us 16. So that one is not correct. Then we can check this one. The constant K is going to be the load, which is 1.8 divided by total extension, which is 0.07 in parallel plus 0.15. So we have 0.075 plus 0.15. So let's add this and see. So we have 1.8 divided by, open brackets, 0.075 plus 0.15, close the brackets, that gives us 8. So this is 8, 0.075 plus 0.15, that gives us 8. So our answer is going to be C. I cannot take D. But for D, this will be 0.075 plus 0.075. That will be the effective constant, I mean extension. The constant here would be 2.4 divided by the sum of these two, because they're in the system is in parallel. So the total extension is just going to be 0.075 plus 0.075. So you have 2.4 divided by 0.075 times 2. This will also be 16. Okay. A metal wire is stretched to breaking point and the force extension graph is plotted. Which graph is correctly labeled with elastic region, plastic region, and the area representing the work done to stretch the material until it breaks? Which graph is correctly labeled? So of course by just looking, this one is wrong, this one is wrong, because they have shared the area under the work done until the material breaks is only this part here. Here they have ignored this area here, so this is also wrong. So we have to choose between the B and the C and the D because the area is correct, showing the work done until the material breaks. It is the whole area under that graph. But then the elastic region must be a straight line and must be a straight line from the origin, and the plastic region must be that part where the material does not return to its original length. So it means our answer is going to be precisely D, because for the elastic region it comes from the origin, the material can return to its original length. The plastic region, the material undergoes an extension where, when the deforming force is removed, it does not go back to its original length. So the answer is going to be D. Which expression equals stress on a wire? Stress is force over cross-sectional area, so the answer is B. A wire is stretched by applying increasing values of force F. For each value of force applied, the extension X is recorded. A force extension graph is plotted from the data obtained. Which statement about the area under the graph must be correct? So we have force against a force extension graph. So force against extension is plotted. Which statement about the area under the graph must be correct? Of course, it can be calculated as a half fx, okay? But suppose the graph does not start from the origin. It may be starting from a certain value, so it may not always be a half fx. The y is stretched by applying values of force F. For each value of force applied, the extension X is recorded. A force extension graph is plotted for the data. It is the elastic potential energy stored in the stretched sample. Elastic potential energy stored in the stretched sample. It is the work done in stretching the sample. So the most appropriate is going to be C, because we don't know until what point is the force applied. It could have been applied beyond the elastic limit. Note that if it is not applied, if the material is not stretched beyond the elastic limit, still the work done in stretching the sample is simply going to be the elastic potential energy. But if the material is stretched beyond the elastic limit, then the work done is not the elastic potential energy. For the elastic potential energy will only stop at where the straight line stops. Therefore, our best answer, all answers look to be correct. It will be the same for any wire of the same material. All answers look to be correct, but the area is going to be the work done in stretching the sample, because we don't know whether it is stretched beyond the elastic limit or not. So the most appropriate would be the work done in stretching the sample. This question is quite technical because this may appear very correct. This could also be appearing correct. Even the last one could be appearing correct, but the most appropriate is C, because all the others could be considered to be subsets. The spring constants of four springs are determined by plotting the following graphs of force against extension X. So the first one, which order of graphs show decreasing spring constant? So K is going to be force over extension. So let's just check here. Here it is going to be 10 divided by 5. Here it is going to be 20 divided by 4. Here it is going to be 100 divided by 0.1. Here it is going to be 10 divided by 0.5. And I think this is the largest. So 3 is the largest. 3 is the largest, this is out, this is out, this is out, meaning the answer is going to be B because 3 is the largest. 100 divided by 0.1 is bigger than the rest, so the answer is going to be B. You can even check the smallest as 1. 10 divided by 5 millimeters, that is, I think, 2 newtons per millimeter. This one is 5 newtons per millimeter. This will be 20 newtons per millimeter. So the answer is going to be B. A steel bar of circular cross-sectional area of circular cross-section is under tension T. The diameter of the wider portion is double. So if this part is D, this is twice D. What is the value of stress in the wider portion over stress in the narrow portion? Of course, we know that stress is equal to force over area. Since area is pi d squared over 4, so this is going to be 4F divided by pi d squared. So I'm just going to divide. For the wider portion, the stress is going to be 4 times the force is T divided by pi. The diameter there is twice D, but this is squared. Then divide by, for the narrow portion, the force is the same, 4T divided by pi. The diameter there is D squared. So this is the same as having 4T over pi times 4D squared. Then times, I get the reciprocal, pi D squared divided by 4T. So 4T cancels, pi cancels, D squared cancels, and I remain with 1 over 4. 1 over 4 is 0.25. So our answer is going to be A. Two guitar strings are stretched by tensile forces. String X is stretched by a force F that causes an extension X. String Y is stretched by a tensile force to F that causes an extension twice X. The springs obey Hooke's law. What is the ratio strain energy in stretched string X over strain energy in stretched string Y? So we know that strain energy is going to be equal to a half force times X. So we are just going to come up with a ratio. So the ratio is going to be equal to, in X, it will be a half. The force in X is just F, and the extension in X is still X. Then divide by, in Y, the force, this is going to be a half. The force in Y is twice F. The extension in Y is twice X. So we shall just cancel out. A half has cancelled, F has cancelled, X has cancelled. So I have 1 over 4. So the answer is going to be D. A spring is initially neither compressed nor extended. A force can be applied to the spring so that it is either compressed, so there's a compression to a shorter length, or extended to a longer length. What is the change in the elastic potential energy in the spring when it is extended and when it is compressed? If it is compressed by the same length or extended by the same length, it means the elastic potential energy is the same. If it is compressed, the elastic potential energy increases. If it is stretched, the elastic potential energy increases in both cases. So let's see the change in the elastic potential energy. Spring is extended, it increases. Spring is compressed, it still increases. So the answer is going to be D. When the spring is extended or stretched, the elastic potential energy increases. When the spring is compressed, still there is elastic potential energy stored, which increases as the compression increases. So the answer is going to be D. Because elastic potential energy is a half k x squared. X can be compression or an extension, so it increases in both cases. The stress sigma in a material is given by this force over area. The strain is in the same material is given by x over L. Which expression gives the Young modulus? So just combine. Young modulus is equal to stress over strain, which is equal to force over area times, we get the reciprocal, L over extension X. So this is going to be FL FL times L over X. We don't have this here, but we have we have epsilon over sigma. That's not Young modulus, it is the other way around. Fx over AL, this is not correct because it is supposed to be FL over AX, so this one is not correct. Then stress times X over L, this is also not correct. It would be, at least it will be stress times L over X, because it is stress over strain. So it is stress sigma divided by X over L, where the L goes up. So this is not correct. So the answer is going to be this one here, which is stress over strain, that is F over A, then divided by epsilon, which is going to be in the denominator. So the answer is going to be D. What is an example of plastic deformation? A rubber ball is momentarily compressed every time it hits the ground. Of course, that is not plastic because it returns to its original shape. A spoon stirring some coffee in a ceramic mug hits its surface and makes a clicking sound. That is not plastic. A toolbox is left on a horizontal plank. When the toolbox is removed, the plank is no longer straight. So the answer is C. It means the plank has retained some extension. A metal wire fixed at one end has length L and cross-section area A. The wire extends a distance E when mass M is hung from the other end of the wire. What is an expression for the Young modulus E of the metal? So Young modulus is going to be stress, which is force over cross-section area, then times or divided by extension over original length, which becomes original length over extension. So remember the force, they have given us mass. The force is going to be the weight. So this is going to be mg times original length divided by cross-sectional area times extension, which makes the answer to be B. The answer there is B. A spring has a spring constant of 6 newtons per centimeter. It is joined to another spring whose spring constant is 4 newtons per centimeter. A load of 80 newtons is suspended from this composite spring. What is the extension of the composite spring? So let's just find extension for each. Here extension is going to be the load F over constant, which is going to be the load here is 8. It experiences a load of 80 over the constant, which is 60. Which is 6 newtons per centimeter. So our answer here is going to be 80. Of course, this is in centimeters. 80 divided by 6. Let me just write 40 over 3 in centimeters. Then here extension is going to be the load again, which is 80 divided by constant, which is 4. And I think this gives us 20. This is 20 centimeters. So total extension, because the series which I just add 40 over 3 plus 20. So I'll say 40 over 3 plus 20, which gives us 33.3. So this gives us 33.3 recurring in centimeters. So our answer is going to be D. The graph shows the extension of a sample of a type of rubber as different loads F are applied and then gradually removed. What is the best estimate of the strain energy in the rubber when a load of 80 newtons is applied? So for a rubber, the strain energy is going to be the area under the graph, because for a rubber, it does not follow a straight line relationship, but it doesn't go beyond the elastic limit. If it remains elastic, so we can find the strain energy by finding the area under the graph. So between for 80 newtons, total extension is 16. So we are going to find the area in this part here. The area in this part here. So we can find first of all an estimate by drawing a straight line here. So if the answer is 80 times 16, it means it included the whole of that area. Let's check. 80 times 16 exponent -3 because it is in millimeters. So 1.2, so this one is wrong. This means it has included the other part up there. So 80 times 16 times 10 power -3. Remember, strain energy is going to be equal to the area under the graph. The area under the graph. The area must be less than 1.3 joules. So D is wrong. If the answer is also less than equal to the area of the triangle, it will also be wrong. Let's check. The triangle is going to be a half. For the triangle, it is a half. For the triangle, area of the triangle is going to be a half times 16 times 8. So a half times 16 times 8, of course, there is times 80. 16 was Newton, was in millimeters, so I will say times 10 power -3 for 16. So this is going to be a half times 16 exponent -3, then times 80, that is 0.64. So 0.64 and less, those are wrong answers. This one is giving us 0.64. It is just for the triangle. It means this part here has been left out. This part here has been left out. So any answer which is less than, which is 0.64 and less is wrong. So our answer is going to be C. Note how I have eliminated the other answers. I first took the area of the whole rectangle here, and it was 1.3, which is big. That one is wrong. Then I drew a triangle inside, and I got its area as 0.64 joules, which means there's a small part remaining there, which has not been concluded. That means 0.64 and less must be wrong. The answer must be above 0.64 and must be less than 1.3. So answer is C. A composite rod is made by attaching a glass reinforced plastic rod and a nylon rod end to end, as shown. So it's like they're in series. Same, they are going to have the same, they're having the same cross-sectional area, I guess. The rods have the same cross-sectional area and each rod is 1 meter long. The Young modulus of EP of the plastic is 40 gigapascals, and the Young modulus EN of the nylon is 2.0 gigapascals. The composite rod will break when its total extension reaches 3.0. So at this point, I'm going to write an equation which is total extension, E total, which is going to be the extension of the nylon plus the extension of the plastic should be equal to 3. This should be equal to 3 times 10 power -3 meters. What is the greatest tensile stress that can be applied to the composite rod before it breaks? Now note very carefully that the same load is applied to this composite material, and they have the same cross-sectional area. So that means they have the same stress. So same force is going to be applied. They have the same cross-sectional area, which implies that the stress is the same. So stress is the same. And remember, Young modulus is equal to force or stress over strain. So since they have different length, they may have different cross-sectional, extensions because of difference in Young modulus. So this is going to be stress. The stress will remain the same. Where there is epsilon, I'm going to put there times or divide by extension over original length, which becomes stress times original length over extension. That's the Young modulus. Therefore, the extension is going to be equal to the stress times original length over Young modulus. So let's come up with this equation. Extension of N, remember, extension of nylon plus extension of plastic should be equal to 3 times 10 power -3. So extension of nylon will be the stress sigma times the original length of nylon, which is 1 meter, divided by the Young modulus of nylon, which is 2 times 10 power 9, because it is giga. Then plus For plastic, remember the stress is the same, so sigma times the original length, which is 1, divided by the Young modulus, which is 40 gigapascals. So it is 40 times 10 power 9. This should give us 3 times 10 power negative 3. So we have only one unknown here. So sigma, therefore, is going to be equal to 3 times 10 power negative 3 divided by, open brackets, 1 over 2 times 10 power 9 plus 1 over 40 times 10 power 9. So this gives us 1, I'll just say 1 divided by 2 exponent 9 plus, again 1 divided by 40 exponent 9. So that is what I have for the denominator. I first solve the denominator. So I will have 3 exponent negative 3, then I divide by the answer, which is giving me 5.7. It is 5.7 times 10 power 1, 2, 3, 4, 5, 6. So this is 5.7 times 10 power 6 pascals. Is it 5.7? 1, 2, 3, 4, 5, 6. Okay, 5.7 times 10 power 6. So the answer is going to be B. Note carefully how I arrived at this. First of all, I came up with an expression for Young modulus. Then, from that expression for Young modulus, I also knew that total extension had to be 3 times 10 power negative 3. Remember, the stress was the same because the same load is going to be applied if they're in series like that, and they have the same cross-sectional area, so the stress is the same. So the answer is going to be B. The graph shows the nonlinear force extension curve for a wire made from a new composite material. What is the best estimate of the work done in stretching the wire to point P? We have done a similar question above. So if we can first find, remember work done is going to be the area under the graph. So this for the rectangle, let's say it is 100 times 2 times 10 power negative 3. So this is the maximum, 100 times 2 exponent negative 3, which is 0.2. So anything above 0.2 is obviously wrong. So 0.2 is not the answer, remember? But this is the area of the rectangle. It should be less than 0.2. So the work done should be less than 0.2 joules. Let's also draw a triangle inside because work done must be greater than the area of that triangle. So we can draw a triangle inside there. So for the triangle, area of a triangle for the triangle, area is going to be a half times 100 times 2 times 10 power negative 3, which is equal to 0.1 joules. The work done should also be greater than 0.1 joules because 0.1 is just for the triangle. So 0.09 is wrong, 0.1 is also wrong. We have already said 0.2 is wrong because the work done should be less than 0.2, but should be greater than 0.1. So our answer is going to be C. A 0.8 meter length of steel wire and a 1.4 meter length of brass are joined together. The combined wires are suspended from a fixed support and a force of 40 newtons is applied as shown. The Young modulus of steel is 2 times 10 power 11. The Young modulus of brass is 1 times 10 power 11. Each wire has this cross-sectional area. The wires obey Hooke's law. What is the total extension? ignore the weights of the wire. Okay, so first of all, we know that Young modulus is equal to stress over strain, which is going to be force times the original length over cross-sectional area times the extension. So they gave us cross-sectional areas. So extension is going to be equal to, I'm making E the subject, is equal to force L naught over area times Young modulus. So now, because they are in series, total extension is going to be the sum. So I'll say E total is going to be, for the first wire, the force is 40, original length, the original length is for the first wire of steel, original length is 0.8. So I'll say times 0.8 divided by the cross-section area has been given as 2.4 times 10 power negative 6. The Young modulus of steel is 2 times 10 power 11, then plus. For the second wire, the load is still 40. The original length of the second wire was 1.4. So this is times 1.4. Divide by the cross-sectional area is 2.4 times 10 power negative 6, then times 1 times 10 power 11. So we're just going to sum up these values. Let's start with the first one, 40 times 0.8 divide by 2.4 exponent negative 6. I'll put the brackets again. I divide by 2 exponent 11. So for the first y, it is 0.0006 recurring. So which is going to be 6.67. I would say this is 6.67 because it is recurring, times 10 power negative 1, 2, 3, 4, 5 times 10 power negative 5 plus, for the other y is 40 times 1.4 divide by, open brackets, 2.4 exponent negative 6, again divide by 1 exponent 11. So that is 2.3 recurring, so that is 2.33 times 10 power 1, 2, 3, 4. So 2.33 times 10 power negative 4. Now we are just going to add. So 2.33 exponent negative 4 plus 6.67 exponent negative 5. So this is 2.997 exponent negative 4, which is approximately 3.0 times 10 power negative 4. So this is 3.0 times 10 power negative 4 in meters. Therefore, our answer is going to be B. A wire X is stretched by a force and gains elastic potential energy E. The same force is applied to wire Y of the same material, so they have the same Young modulus. I'll use Y for Young modulus. With the same initial length, but twice the diameter, same initial length L, but twice the diameter of wire X. Both wires obey Hooke's law. What is the gain in elastic potential energy of wire Y? Okay, so Young modulus, I'll use Y for Young modulus. Young modulus is force over area times original length over extension. Because area is pi d squared over 4, so Young modulus becomes 4 F L naught divided by pi d squared times E. So that is the Young modulus. And the Young modulus is the same because it is the same wire. So I'll just say this is equal to, let this be for wire X. This is for a wire X. So for wire Y, it is going to be 4F. They have the same original length, so times L naught divided by pi. But for wire Y, the same force is applied. That's why I put the F to wire Y. Same material, same Young modulus with the same initial length, but twice the diameter of wire X. So where there is diameter for wire Y, I will put there twice D and T squared. Both wires obey Hooke's law. Both wires are obeying Hooke's law. So this will be the extension. If this is E, the extension of the second wire Y is going to be EY. Okay. So let's cancel out some of these things. Note that I've equated the two equations because Young modulus is the same. So I've got an expression for Young modulus for wire X and an expression for Young modulus for wire Y. And since the Young modulus is the same for the same material, I've just equated. So these ones cancel out. Pi cancels. D squared also cancels. So I remain here with a 1 over E is equal to 1 over 4 because I have cancelled out D squared. This becomes 2 squared times EY. So it means that the extension of wire Y is going to be phi cross multiply. The extension of wire Y is going to be a quarter of E of the original extension. So the question is, what is the gain in elastic potential energy of wire Y? Remember, elastic potential energy, which I will call E for Y, is equal to elastic potential energy is equal to a half F times the extension of wire Y. So this is going to be a half times the same load is applied, then times the extension for wire Y, which is a quarter of E. When I pull out a quarter, this will be a quarter times a half Fe. Remember, the elastic potential energy for wire X was simply a half Fe. So a half Fe is going to be capital E, so this becomes a quarter times capital E, which a quarter times capital E is 0.25 times E. So our answer is going to be A. Of course, I do this the long way, but I know good mathematicians don't do all these steps. They just use constants, and the constants cancel out. So, but that is the answer is going to be A, 0.25 E. The strain graphs for loading and unloading four different materials are shown. Which material exhibits purely elastic behavior? Which material exhibits purely elastic behavior? So elastic, it should go back to its original length. So this one is not elastic, it is not going back to original length. This one is not elastic. This one is also not elastic. So the answer is B, because on loading, the material stretches. On unloading, it goes back to its original length. So the answer is going to be B, purely elastic behavior. Four solid steel rods, each of length 2 meters and cross-sectional area 250 millimeters squared, equally support an object weighing 10 kilonewtons. The weight of the object causes the rods to contract by 0.1 millimeters. The rods obey Hooke's law. What is the Young modulus of steel? So let's try to sketch this. If maybe by sketch it is easy. So we have four rods shown here. The weight of the object causes the rods to contract. So there's an object on these rods. Therefore, it's like having four springs in parallel. What happens to the extension? The extension, they have said the rods contract by 0.10 millimeters. That means if it was used alone, it would contract by 4 times this extension here, this contraction. So I am saying if used alone, the rod contracts by 0.1 times 4, which is 0.4 millimeters if it was used alone. Remember, like when you have springs in parallel, their total extension, their effective extension is a quarter the extension of 1. So if it was 1, it would be 4 times the total extension. So let's find the Young modulus. Young modulus is equal to stress, which is force over area, then times original, of course I get the reciprocal of strain, which will be original length. This is original length over, what has happened to the pen? Sorry, my pen has jammed. I don't know what has happened. Okay, so this is going to be times what is the Young modulus? So it is going to be original length over extension. Okay, so we want to find the Young modulus. The load has been given as 10 kilonewtons. The load has been given as 10 kilonewtons, so let's write here 10,000 newtons, then times the original length is 2 meters, divided by the cross-section area was given as 250, but it has to be changed to meters squared, so it is 250 times 10 power negative 6. So this is going to be 250 times 10 power negative 6. Then times the extension. They say the wire of the object causes the rods to contract by 0.1, and we have seen, because I want to find Young modulus of steel, I'll just use one rod, not all of them. So if I'm using one rod, it will contract by 0.4. So this will be times 0.4 times 10 power negative 3. So this is going to be 10,000 times 2 divided by 250 exponent negative 6, then divide by open bracket 0.4 exponent negative 3. So this is giving me a 2.0 times 10 power 11 pascals, which means our answer is going to be precisely B. The wire is attached at one end to a fixed point. A tensile force F is applied to the other end of the wire, causing it to extend. This is shown on the graph by the line OSP. The force F is then gradually reduced to 0 and the wire contracts. This is shown on the graph by the line PQ. Which area on the graph represents the work done by the wire as it contracts? Let me change the color, maybe this is not visible. So as it stretches, the area is going to be OSPRO as it stretches. Then as it contracts, the area is going to be QPRQ. So QPRQ, that is unloading, or as it contracts. So the answer is going to be C. Which area on the graph represents the work done by the wire as it contracts? So that is QPRQ. A mass attached to the lower end of a spring bounces up and down. At which points in the path of the mass do the gravitational potential energy of the mass, the elastic potential energy in the spring, and the kinetic energy of the mass have their highest values? Because if it bounces up and down, it means automatically kinetic energy is maximum when it is passing equilibrium. So kinetic energy is maximum when it is passing equilibrium, that is at the middle point. So kinetic energy is maximum at the middle point. So this at the top it is 0, at the top it is 0. Kinetic energy is maximum at the middle point. Kinetic energy is maximum at the middle point. Then the gravitational potential energy is maximum at the top because it depends on mgh. So gravitational potential energy is maximum at the top. So A has already been cancelled out, D has already been cancelled out, and we are saying gravitational potential energy is maximum at the top. So it means our answer is going to be C because B is showing bottom. Elastic potential energy is, of course, for elastic potential energy, it can be maximum at the bottom or the top. But since for gravitational potential energy, it is only maximum at the top, then it means our answer is going to be C. Top, middle, these are the most important points. For elastic potential energy, I'm saying it can be maximum at the top or at the bottom. But since gravitational potential energy is maximum at the top, so it means our answer is C as compared to B. A tensile force is used to extend a sample of a material. The force is then removed. The variation with the strain of the applied stress is shown on the graph. Which point on the graph could represent the elastic limit for the material? Elastic limit for the material. This one is proportionality limit. Remember, after the elastic limit, the material enters the plastic deformation. So the answer is automatically B, because after B, the material enters plastic deformation. So the answer is B. A tensile force is applied to an unstretched rubber band, causing it to stretch. The tensile force is then removed. Which statement about the rubber band must be correct? If the rubber band stretches elastically and plastically, all the work done by the force is converted to thermal energy. That is not true. It is only when if it stretches elastically and plastically, not all the work is converted into, because this means it does not return to its original length. If the rubber band stretches elastically, it obeys Hooke's law. Not at all. It does not obey Hooke's law. If the rubber band stretches elastically, the gradient of the force extension graph represents the work done by the force. That is also not true. If the rubber band stretches plastically, the rubber band will be longer after the force is removed than it was before the force is applied. So that is going to be true. For plastic deformation, the material retains some extension. So it will be longer after the force is removed than it was before the force was applied. A spring is attached at one end to a fixed point. A mass is then hung from the other end of the spring. The spring has extension X when the system is in equilibrium. The variation of the tension in the spring with its extension is shown on the graph. Which statement is correct? Area SPR represents the energy stored in the spring which cannot be recovered. SPR represents the energy stored in the spring which cannot be recovered. We are seeing a straight line, so here it means energy can be recovered, so I can ignore this one. SPQR represents the energy stored in the spring which can be recovered. SPQR, that is also not true. That is the area of that square. It is not the energy stored in the spring. Area SPQ represents the loss of gravitational potential energy of the mass due to the extension of the spring. SPQ represents the loss. SPQ represents the loss in gravitational potential energy of the spring. That is also not correct. Then area SQR represents the elastic potential energy stored by the spring. That is very correct. Area SQR is elastic potential energy. Remember, I said the area is always with the extension axis. So the answer is going to be D. An elastic cord of unstretched total length of 16 centimeters and cross-sectional area 2.0 times 10 power negative 6 is held horizontally by two smooth pins a distance 8 centimeters apart. So this is 8 and 8 up, giving us a total of 16 centimeters. So original length is 16 centimeters. Then the stretched length, I'll call it L. It will be 8 plus, I think this side is also 8 centimeters, plus 8 centimeters, which is 20, or a straight length is 8 plus 8 plus 8, which is 24 centimeters, which means the extension is going to be 24 minus 16, which is going to be 8 centimeters. So the change in length is 8 centimeters. The chord obeys Hooke's law. The chord obeys Hooke's law. A load of mass 0.4 is suspended centrally on the chord. The angle between the two sides of the chord supporting the load is 60. So I will draw a vertical line here to divide this angle into 30 degrees. So I may need the force here. The force here, let me call that the tension in the chord, because the tension is going to help me to find the force. For equilibrium, the tension upwards, when I resolve T upwards, to be T cos 30. But remember, the two tensions act upwards. So I will say there's tension here, which is T cos 30. There's also tension here, which is also going to act upwards, T cos 30. So I will say twice of T cos 30 will give us the weight downwards, which is 0.4 times 9.81. That is the force downwards. So this is going to be equal to 0.4 times 9.81. So it means the tension in the chords is going to be 0.4 times 9.81 divided by 2 cos 30. So that is the tension. Now I want to find the Young modulus. So let me first find the tension. 0.4 times 9.81 divided by 2 cos of 30, which is 2.27. So this is 2.27 newtons. So to find Young modulus is going to be force over area times original length over extension. So this is going to be the force, which is 2.27. The original length was 16 centimeters, so I'll say 16 times 10 power negative 2 divided by the cross-section area, which is 2.0 times 10 power negative 6. The extension is 8 centimeters, so that is 8 times 10 power negative 2. So this one has cancelled. So you have 2.26, so 2.27 times 16 divided by the denominator I have 8 times 2 exponent negative 6, which is 2.27 times 10 power 1, 2, 3, 4, 5, 6 times 10 power 6. So it is approximately 2.3 times 10 power 6 pascals. So our answer is going to be C. A student is investigating the mechanical properties of a metal. He applies different loads to a long thin wire up to its breaking point and measures the extension of the wire for each load. He then plots a graph of stress against strain. The gradient, remember, of this graph, the gradient is equal to Young modulus. The gradient is Young modulus. The student repeats the experiment with a wire made from the same metal. This is very important. If the wire is made from the same metal, then the Young modulus E is the same. Young modulus is the same, with twice the original length and half the diameter. So the length is twice the original length and the diameter is half d. But remember, it is the same metal and it is a graph of stress against strain. The Young modulus is the same and the gradient is the Young modulus. So which graph is obtained? This one is showing not the original graph, first of all, not the original graph, the scale here and the scale here. So if it is the Young modulus is the same, the gradient of the graph should be the same. So you must look at the gradient. So here the values on the y remain the same. These ones have been changed. So this is out. The gradient will not be the same. Here the graphs, the values of y have remained the same. The values of x have remained the same. And you look at the graph is the same shape. So this is the answer. Here the values on the x are not the same as before. The values on y are not the same as before, but when you check one of them, you notice that the gradient is not the same. So you can try to check this point here. You notice that the gradient, you can check and see that Young modulus is not the same. So this is out and this is out. The answer is going to be precisely B, because the gradient of the graph should be the same at every point, every corresponding point, because the Young modulus remains the same. Which statement describes what is meant by plastic deformation of a material? Plastic deformation, remember, the material does not return to its original length when the deforming force is removed. So it always obeys Hooke's law. That's not correct. It does not return to its original length when the extending force is removed. So our answer is going to be B. The diagram shows a simplified model of a building with 4 identical heavy floors. They are identical. The spacing of the bottom floor from the ground is twice that of the spacing between the floors. So let's say the spacing between the floors is h. So this spacing is going to be twice h. Between each floor are equal number of vertical steel supporting rods of negligible mass compared with the floors. The rods are of different diameters so that the stress in each rod is the same. Okay, so that the stress in each rod is the same. What is the ratio diameter of bottom rods over diameter of total rods? The stress is the same. Okay, so to find stress, stress is equal to force over area. This is going to be, because the area is pi d squared over 4, this is going to be 4f divided by pi d squared. So we need f. The force experienced by the bottom rods. The force here is we have, if we consider the force on the top by just this one here, let the weight of this be W. So the force on the top, the force here is going to be force on the top is going to be W. Then the force experienced by the bottom, this is going to be W plus W plus W plus W. This is the total force on the bottom. The force on the bottom is going to be 4 times W, because all these floors are exerting a force on the bottom rods. Okay, so we're now going to remember the stress must be the same. The stress, the rods are of different diameters, so that the stress in each rod is the same. The stress in each rod is the same. So to find the stress at the bottom, I will simply say the stress at the bottom, I've got sigma B. The force is, this is going to be 4 times the force at the bottom, which is 4W, divided by pi times the diameter at the bottom, which I'm going to call d bottom squared. And the stress at the top, I'll call it sigma T. This will be 4 times the force at the top, which is W, divided by pi, the diameter at the top, which I'll call dt squared. So we want the ratio diameter of the bottom over diameter of the top. So I'm going to just divide these two equations. So the ratio will be equal to, or let me just divide, because the rods are of different diameters, so that the stress in each rod is the same. So since the stress in each rod is the same, it means I'll equate these two. The stress in the bottom rods is the same as the stress in the top rods, so I will say 16W, that is 4 times 4, divided by pi d bottom squared is equal to 4W divided by pi d top squared. So W has cancelled, pi has cancelled. So I want diameter of the bottom, so I'll take a diameter of the bottom that side. By the way, this by 4 is 4, by 4 is 1. So I cross multiply, I have 4. Diameter of the top squared is equal to diameter of the bottom squared. So I'm going to just divide both sides by diameter of the top squared. So this one has cancelled. So the ratio is going to be the square root. Diameter of the bottom divided by diameter of the top is going to be the square root of 4, which is going to be 2. So the answer is going to be A. The Achilles tendons in a rabbit leg is stretched when the rabbit jumps. The graph shows the variation with the tension of the length of the tendon. What is the strain energy in the tendon? Remember, energy is going to be the area under the graph, but it is the area with the extension axis. Area with the extension axis. So I'll draw, this is almost in the center here. That is almost in the center there. This is also almost in the center. So this is the area which I want. That is the area which I want. So energy is going to be equal to a half times the force is 500 minus 0, that is 500, times the extension. The scale here is 2 divided by 5, which is 0.4. So here it is 34.4.8. That is 35, I think, in the middle. 36.4, 36.8, 37.2, then in the middle it is approximately 34.8, 37.2, approximately 37.6, or okay, 37.6 or 37.4. So this will be 37.6 minus 35. That would be the extension, approximately, because this is not, it is almost at the center, but I can take 1, 2, 3, 4. That is 36.4, 36.8, 37.2, 37.6, approximately 37.6. So this will be 37.6 minus 35, then times 10 power negative 3. So this is going to be, I will start with that very part, 37.6 minus 35. This is an estimate, so we shall get a value very close. Then times 500 exponent, there is a negative to the other side. Then I divide by 2. So this is giving me 0.65. 0.65. Is it 0.65? Okay, I have to check this again. Oh, this is at 400, not at 500. Sorry. Let me check this again. So 400, sorry, this was 400, is in the center here. Okay, so 36.4, 36.8, that is 37 exactly. So this is 37, not 37.6. So that is 37, 37 minus 35, 37 minus 35. This is 37 minus 35, which is 2. Okay, so I'll check this again. So that is 2 exponent negative 3, then times 500 divided by 2, which is 0.5. So it means the answer is going to be A. The most closest answer there is A, because I estimated this one 34.4, 34.8, and in the center here it is 35. So I estimated that one, and this one is also an estimate, so the most appropriate answer is going to be A. So this is giving me approximately 0.5, but the most closest answer there is going to be A, because these values are just estimates. I just estimated this one to be in the middle, which may not be exact in the middle. I've also estimated this one here. If you have a more magnified graph, you can get a more appropriate value. So the answer is going to be A. A wire of circular cross-section which obeys Hooke's law is used to suspend a basket as shown. The Young modulus for the material of the wire is 2.5 times 10 power 11 pascals. When a weight of 34 newtons is added to the basket, the strain in the wire increases by 6 times 10 power negative 5. What is the radius of the wire? So we know that Young modulus is equal to force over cross-sectional area times. They told us that the strain increases by 6.0 times 10 power negative 5. So this will be over, this is going to be Young modulus is force over a cross-sectional area. This is going to be divided by the strain. So this is divided by the strain, which is extension over original length. So this, I'll just put here strain divided by strain. So that is Young modulus. And what is the radius of the wire? So where there is area, this is just going to be pi r squared. Because we want radius, it is going to be pi r squared. So this is going to be equal to Young modulus is going to be force over pi r squared. Then time, I will put the strain at the bottom. So this is going to be times the strain. Okay, so I will substitute. Young modulus is 2.5 times 10 power 11. The force is 34. Divide by pi times the radius squared times the strain in the denominator. Because the strain in the wire increases by 6. So the change in the strain is 6 times 10 power negative 5. So we want to find the radius, so I'll just make R the subject. From my calculator, R will be 34 divided by, okay, those who are not good at math, R is going to be equal to the square root of 34 divided by pi times 6 times 10 power negative 5, then times 2.5 times 10 power 11. That will be our value of R. So 34 divided by, I'll open the bracket, I'll open two brackets, so I'll say pi into the first bracket 6 exponent negative 5, open another bracket 2.5 exponent 11. So that's what I'm getting. Then I find the square root of the answer, which is 8.49 or approximately 8.5 times 10 power negative 4 meters, which means our answer is going to be C. Okay, so I have tried my level best to record part 1 of the formation of solids. If there are errors, please, I'm sorry, I'm bound to make some few mistakes. At some point, I may not explain to your satisfaction. That is natural, because my explanation may not really click into your minds, but I try my level best. Nevertheless, I still believe that you learned something from these videos, and I'll see you in part 2 of the formation of solids. The formation of solids will be strictly 3 parts for multiple choice questions. All the best and enjoy the rest of the day. Bye bye.